Amy Sullivan, and I'm the chair of the AAAR Endowment Committee. And it's my pleasure to welcome you in our 9th in the monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. With this initiative, we hope to be able to provide a venue to be able to share the exciting research happening in our community, to also tie our journal AS&T to other activities, and also give us an opportunity to all come together outside of the annual conference. So each month, the editors of AS&T pick a high impact paper to be presented by its author. These lectures are being recorded and they will be later posted to AAAR's YouTube channel, which you can access from the AAAR webpage under the events tab. In addition, each month, one of our AAAR student chapters is serving as host. And also the student chapters have formed a journal club, which generally meets the week before the lecture to discuss the paper to be presented. So students, be on the lookout for an email about that. And so lastly, I just want to thank everyone who's helped us in making these lectures possible, and also for all of you for joining us. And so with that, I'll turn it over to our student chapter from the University of Florida to get us started. Thanks.
Thank you, Amy, and welcome you all for the session today. And I'm Sri Priya, a third-year PhD student in the Department of Environmental Engineering at University of Florida. And my colleague, William Bradwalls, is a co-host for this lecture. So Joachim is a professor for experimental atmospheric research at Goethe University Frankfurt in Germany. He studied physics and earned his PhD in Heidelberg. He spent 2 years working as a postdoctoral researcher at NOAA in Boulder, Colorado, studying the formation of atmospheric aerosol particles. After a period of serving as a research assistant at the University of Mainz, he was appointed by Goethe University Frankfurt in 2007. He serves as a spokesperson for several coordinated research projects and was named as a highly cited researcher in geosciences in 2018. His research focuses on atmospheric trace gases and aerosols. During the pandemic, he switched his focus to study the reduction of airborne transmission risks by running air purifiers in school classrooms. So in this talk, Joachim will discuss the advantages, practicability, and also the limitations of using air purifiers in schools. So please feel free to post your questions on the chat during the lecture, or you can also unmute yourself after the lecture to ask questions. Brad will monitor the Q&A session. And with that, over to you, Joachim. The floor is all yours.
Okay. Hello and welcome from my side. And thanks for the kind introduction and the invitation. I see that there are still many microphones open. Maybe I could ask you to shut off the microphones. Apparently they were not automatically shut off. Thanks a lot. And I will share my screen so we can start the lecture for today. Okay, I hope you can all see the screen. That's great. Well, this lecture is about testing mobile air purifiers in a real school classroom. Well, all of you are certainly aware about all the discussions that were going on over the past 2 years about how is the transmission of COVID-19 happening, how is SARS-CoV-2 being transmitted. In the beginning, it was very much thought that it's basically large droplets which are doing the transmission, but more and more it became clear that it's actually airborne transmission, and small aerosol particles play a big role as a pathway of transmission. Until today, it's certainly not really clear what is the dominating pathway, but aerosols do play a large role, and small aerosol particles, and even being far away from an infectious person, you can still catch the COVID-19, although or especially if you are in a closed room and there's low ventilation basically happening. And over time, I think the other routes like foamid transmission and so on became less and less important. whereas it became clear that aerosol transmission is really the most important thing. There was this big debate about aerosol versus droplets, especially in the US. I think many people there, Jose Jimenez, Lindsay Moore, and Moravska, and so on, and then Kim Prather pushed forward that this understanding, mostly from the medical world, that aerosols are tiny, smaller than 5 micron particles which can float around, whereas droplets are large enough to sink to the ground very fast. This paradigm has shifted somewhat, and it became clear that 5 or 10 micrometers is not a very good measure, although it had been used in the medical world for a long time to distinguish between aerosol particles and droplets. But it's not really a good measure, because even 50 micron particles, for example, do not sink to the ground very fast. They can still float around for minutes. And so actually the difference between particles that float and droplets that actually sink to the ground very fast should rather be drawn at diameters of around 100 microns. And this is from the early days 2 years ago. In March 2020 already, there was a publication saying from a call center in South Korea, finding that SARS-CoV-2 was transmitted to more than half of the people sitting in one room there in this call center. So many people sitting together for many hours of the day, and they certainly didn't all get into contact with the index person within 1.5 meters. This was certainly a very good case, or actually to make the case that this is airborne transmission. And this was just one out of many examples, the famous choir rehearsal and so on, were showing the same thing. Okay, and as you are all studying aerosols and aerosol science, actually aerosol physics, a little bit about the way how filters work. Actually, filters do not work like sieves. The modern Hepa filters that are used to remove aerosols from the air, they basically look in a way like you can see down on the lower right-hand side. So you have these fibers on which the aerosol particles attach, and you have the different processes, Brownian motion, impaction, and interception, which lead to removal of the particles which will stick to the fiber. And actually, it's most difficult to remove the particles around 0.2 to 0.3 microns in size. The very smallest particles around 10 nanometers to 100 nanometers, are efficiently removed by their large Brownian motion, whereas 200 to 300 nanometers is really the most difficult to remove. But the high efficiency filters are able to remove almost 100%, like 99.9% is possible if for the air that is going through the filter. But for that, it's important that the air goes through the filter, i.e. you need large flows. Now a little bit about aerosols spreading in a room. We know very well by now that breathing, speaking, singing all freeze particles. You exhale the particles, and these particles may contain some virus. And in the near field around a person, you have a higher concentration, but in a typical setting like classroom, within 1 to 2 minutes, you get a distribution basically all over the room. And due to turbulent mixing, you have convection from the body heat from the students in the classroom. You get a lot of turbulence in the room and therefore rapid mixing. And actually we found that within a few minutes, the aerosol is basically evenly distributed in the whole room, and everywhere in the room, if you measure with CPCs, with condensation particle counters, you find very similar concentrations. And it's very comparable basically to cigarette smoke. And for cigarette smoke, we all have a impression how fast it spreads, and that you can smell it everywhere in the room if one person smokes. Now in the idea basically for this study was to use the well-known mobile air purifiers that can be used to remove particulate matter, to remove allergens and so on from the air, and basically use this as a protection measure against the COVID-19 disease. And so the most important thing is really the clean air delivery rates. You need high rates, and I would recommend something like 1,000 cubic meter per hour, which is 590 cubic feet per minute, for a typical classroom of the size of 180 cubic meter or 6,350 cubic feet. Yeah, if there are questions, please speak up. Unfortunately, I cannot see the chat, but okay. And you should use filters like Hepa filters or PM1 filters, which filter out to have a high efficiency of more than 90% for particles smaller than 1 micron. These filters, which are which you can buy commercially, the typical household appliances, have a fairly simple setup. They all look very similar. They have a fine mesh in the beginning to remove porous particles. Then typically a second filter, which uses activated charcoal to remove some odors. And then what is important for us is the Hepa filter here as the third filter, which removes the fine particles and ultrafine particles. And then there's a blower to drive the air ventilation through the filters, and the cleaned air goes out at the top typically. There are many different brands and many different devices available, starting from basically heavy duty machinery that is typically sold for industrial purposes, but then the household appliances, which you can see here on the lower right. And they have been used for many years in principle. So in Germany, 2 years ago, in the summer 2020, we really had a fierce debate about which measures to implement in order to keep the schools open. We had many weeks of homeschooling during spring 2020. All the schools were closed in order to have social distancing and not too many infections occurring. It was a consensus that we should open the schools as much as possible and should return to schools being open and having the lectures and courses taken in presence. Many persons, then of course you have many persons in one room. They spend many hours per day together. Up till very recently, there was no vaccination for children available. So basically a perfect storm setting for many infections to occur. Additionally, in Germany, basically HVAC systems, heating, ventilation, and air conditioning is not available in most schools. They are typically vented just by opening the windows. Most schools in Germany are quite old, like 100-year-old schoolhouses, and they do not have HVAC installed. So they have heating via water pipe system, and that's it basically. And so there was a huge debate between federal and state level, between state level and communities, between parents, teachers, politicians, and so on, going on about what measures are necessary in order to keep the schools open. And then on top, the German Environment Agency and the Commission for Indoor Air Hygiene, they were back then, 1.5 years ago, really strictly against air purifiers. They were saying there are no studies available whether these air purifiers work in a real schoolroom setting, and they were had doubts that they would work properly, and this would just be a commercial interest for if people were advertising or were actually recommending air purifiers to be used. And because there were no studies available, we decided to actually conduct an independent study as fast as possible at a school in Germany. So this was in August 2020 and was basically when we started the work, and this is what led us to the ASNT paper that then appeared in February 2021. And as you can see here, by now it's received almost 32,000 clicks or views. It was referenced 21 times, and the altimetric score is 2,763. And this altimetric score basically looks at the how much is a paper distributed via Twitter, via other means, blogs and Facebooks and so on. And because there were so many parents and teachers and so on concerned about the schools, this paper really reached a lot of attention rapidly, and it was by far not the most difficult study I've ever done. Actually, it was fairly simple study, but of course it was of very high topicality and very high interest in the public, and therefore it was really an important study in hindsight, and for ASNT it is the #1 in terms of altimetric score at the moment. So what did we do? Actually, we went to a school in Wiesbaden, which is nearby here. It's actually the school that my children attend. And so we talked to the dean, we talked to the school, to the parents, and most of all, we talked to the Ministry of Education and asked them to allow us to do these measurements. This was almost the most difficult thing, to convince the ministry that we could do it at our own cost. And then we went to one of the schoolrooms and installed 4 of these Philips air purifiers at positions 1, 2, 3, and 4. And we had aerosol instrumentation, several CPCs, condensation particle counters at different positions, an SMPS system to measure the aerosol size distribution, and an OPS system to measure the larger aerosol particles. So that was basically it. We had 26 students in the room and 1 teacher plus 1 scientist to do the measurements. and we were just running for 1 week of classes in presence and measuring the aerosol distribution. This is the school where this took place. You can see that actually it's an old building from 1904, so no HVAC system, just ventilation by open windows. And we actually conducted this study in this room here. This is a photograph of Manuel Granzin from our group, a PhD candidate who did actually do the measurements. And you can see the windows here, and this is one of the air purifiers in the room. So what did we do? This is just a day of measurements, and we actually had 2 rooms. We had 1 room where the 4 air purifiers were installed, and what you see here in blue is the measurements that took place in the room next door, which had no air purifiers installed. The time down here is UTC, so German time is 2 hours behind that, or yeah, before. So it was, school is not starting at 5:30, but at 7:30. Basically, the doors are opened and aerosol from the outside comes in. Windows are also opened, and then at shortly past 8, the doors and windows were closed. And then basically in the 1 room, only by breathing and natural decay, that's the blue line, aerosol particle concentration dropped. And in the other room, aerosol particle concentration dropped much faster because the purifiers were running. And they were running at stage level 3, O3, during in this case. And then you have a break and ventilation going on again, windows are opened, and then next lesson takes place, and again, same thing, particle concentration drops exponentially, and you have the slow natural decay and the much faster decay for the room where the air purifiers were running. And so from hour to hour, we lesson to lesson, we switched settings. On this day, we ran with 4 purifiers and used either mode 3 or turbo mode. Of course, when windows or door were open, then aerosol from the outside is coming in, the particulate matter is coming in. So in this case, you have hardly a reduction, but whenever you have these exponential decays, you can actually calculate how fast the reduction in aerosol is taking place. And you can basically calculate the clean air delivery rate for these rooms, for these settings, and calculate how fast the aerosol is removed. You get a very homogeneous reduction. As you can see, the red and the black line really closely overlap whenever these purifiers are running, and they were positioned at different parts of the room. So in all the in every area of the room, basically the same concentration is present, and it's reduced evenly in the entire room. Typically, we saw more than 90% reduction within 30 minutes. When we switched to the turbo mode, we could even go down even more than 90% within 30 minutes. Okay, so we did a number of these measurements with different settings, 3 purifiers, 4 purifiers, running them in different modes with different clean air delivery rates in total, 770, 1026 and 1400 cubic meters per hour. And you can see if you normalize to a standard concentration in the beginning, you can see the concentration drops more than an order of magnitude within less than 30 minutes for these 2 settings with the turbo or with 4 purifiers in the black and the red mode, compared to without purifier, where it would go down 20 or 30% within half an hour. Actually, in part due to the fact that 30 people are breathing in there and therefore also filtering out some of the particles out of the air, but also because natural sedimentation and so on occurs. So, of course, just letting air particles in through windows and then looking at the decay is not exactly the same setting as a person spreading aerosol particles continuously. And we also looked at this experimentally, but I'm here showing you just the what we calculated. If a person is emitting continuously once in a room without any purifiers running, it's just a closed room and the person is constantly speaking, constantly emitting, and then you have a constant emission, and the concentration in the room will rise linearly. That's the red line. If you have an air purifier running at a certain rate of removal, quite quickly you reach a steady state concentration. That's the blue here, and basically that's when there's an equilibrium between the person constantly emitting and the purifier constantly removing particles. You get at some level a equilibrium, and this is here shown in blue after some time, and basically the difference between the two situations with and without purifier is constantly increasing then. Until also at some point also this red line will go into an equilibrium, but we didn't look at that in detail. Then the dashed line here shows basically the inhaled dose for both these cases. So the inhaled dose is basically just the integral for the red line. So the inhaled dose in the case where you have no purifier running is increasing quadratically. So the longer you spend in the room, the more you will take up in terms of RNA containing aerosols, or basically viruses. And therefore, the more likely that you become infected. In the blue case, when you have the air purifiers running, you are breathing this constant concentration over time, and then the increase is linear, as you can see here in the blue case, and it's the difference again between the two dashed lines is becoming larger and larger. And after 2 hours in a closed room, basically this difference is about a factor of 6 between without purifiers and with purifiers. Okay, so important message here, the infection risk increases over time, and it's in quadratic increase for the case where you have no ventilation and no purifiers. And after 2 hours, you have about a factor of 6 difference here for the clean air delivery rate that we used of somewhat above 1,000 cubic meter per hour. And this is again to illustrate this a little more. On the left-hand side, we have basically discussed just a moment on the last slide. Basically, if you have no venting of the room and then with air purifiers. And on the right-hand side, I also added the use of ventilation. Actually, if you open the window every 20 minutes and you have a very efficient ventilation, large difference in temperature between the outside air and the indoor air, or big wind outside bringing in fresh air very rapidly, then the concentration drops immediately, and then you close the window and it starts rising again because the person emitting aerosols is always emitting. That's the assumption here. And then this is the blue line, and the orange line is basically adding again aerosol purification with 1,000 cubic meters per hour. And on top, doing the ventilation every 20 minutes. So every 20 minutes, you open the window and it's additionally reduced. The amount of virus-containing aerosols is additionally reduced by the opening of the windows. So you can clearly see the worst you can do is sitting in a closed room without ventilation and without air purification. Second best is basically running air purifiers or just venting. And then the best thing you can do is combining both air purification and venting. Okay, and this is what we also published in the ASNT in the supporting online material, where we compared these three situations. And for concentration, and then also what is a little bit easier to see here now for the dose that you take up by breathing in this room. And then you can see if you don't do anything in a closed room, you have this quadratic increase. Then inefficient venting, air purifier, or efficient venting are about the same in terms of dose uptake. And then if you combine the measures, do venting every 20 minutes and air purification, then you have the lowest dose uptake. It doesn't go to zero, so there's still a risk of getting infected, but the risk is much lower compared to no measures. Okay, one additional thing to talk about here is CO2 levels. Of course, if you are in a closed room, 25 persons breathing, then CO2 in the room goes up. And actually, I was surprised to see how dramatically it goes up if there is no ventilation. So you easily get up to levels of 2,000, 2,500, almost 3,000 parts per million within one school lesson in such a room. And actually the advice since many decades is to stay below 1,000 part per million, because concentration is worsened, people get sleepy and so on. I realized why I was always tired in school back in the old days. We certainly didn't have enough ventilation and not enough fresh air. So actually, it's important to state that you cannot replace ventilation by air purification, because the air purifiers do not clean out the CO2. Of course, they cannot, and therefore, in order to get rid of the CO2 in the room, you need to provide fresh air, and you need to get rid of the CO2 by ventilation or other methods. Another thing we looked at is how long can you use these household appliance Hepa filters and also the pre-filters. Actually, the pre-filters have to be cleaned pretty soon. After 1 or 2 weeks, you need to clean these mesh filters that you see here, because the coarse dust and hairs and so on will collect on these screens, and in order for them not to clog, it's important to clean them regularly. But the Hepa filter actually lasts pretty long, and this is what we studied in a follow-up study, and I want to use the last few minutes to present this to you. Actually, we ran these air purifiers in a schoolroom, first in the lab this was actually measurements in the lab where we checked how this whether they degrade over time, whether with more and more operating hours the filter efficiency would decrease. And actually we saw that it's pretty stable. They lose about 15% over close to 2,000 hours of operation. So that was the first test with using just ambient air. So these are ambient PM levels in Germany around 15 to 35 micrograms per cubic meter. And over these 2,000 hours of operation, the air purifier dropped in efficiency by, or the CADR, the clean air delivery rate, dropped by about 15%. We did the same thing in a school. This was a school, an elementary school, where we ran also Philips air purifiers for about half a year. Every school day while school was taking place, they were run for 5-6 hours. You can see the measurements are not as precise because oftentimes doors were opened or similar things. But what we actually found also here over this half year of operation in real class, the clean air delivery rate dropped by about 15%. And actually the specification by the manufacturer, which is this dashed line here, was still fulfilled because the manufacturer actually quotes the clean air delivery rate, which is a little bit lower than what is actually delivered by the instrument in the very beginning, as you can see here. We also tested this with another device. This was one of these heavy-duty, quite expensive instruments from another manufacturer. And here you can see again it fulfills the clean air delivery rate as given by the manufacturer, and basically in these two cases we had higher values because there was also some additional air supplied to the room through a ventilation system in these two rooms that were in this school where we did these measurements. And again, over many operating hours, 1,400 operating hours, basically the clean air delivery rate was quite constant. So they do not lose efficiency over time, at least not too much. Another question that is also often asked, whether these kind of plexiglass walls are recommended. I'm quite reluctant about those. Well, yes, they do help to prevent droplets from spreading. So if somebody is sneezing or so, this can be helpful. But as we all know, aerosols do basically travel by them, and cigarette smoke or something similar would also spread in the whole room, whether you have plexiglass walls or not. So, and actually the free circulation of air is hindered a little bit. So if you have open window or air purifiers running, actually the cleaning of the air is not as efficient. So I would actually not advise to use these in classrooms. Okay, and one last thing. I think what is going on in Germany but all over the world is somewhat a paradigm shift. For water, for decades, we have been expecting drinking water quality for tap water, and that this tap water is free of pathogens. I think in the future, this will also apply for indoor air, that we expect that the levels of pathogens, particulate matter, allergens, have to be reduced to guarantee healthy conditions in schoolrooms, in offices, and so on. And I think this is quite an important development that was brought about by the pandemic. And I think things like filtering the air will be done much more in the future. Actually, our air cleaners now used everywhere in Germany. Well, we had an ongoing debate for many months. Some states adapted it. Bavaria, Hamburg, Bremen, Berlin did buy air purifiers for schools over the past years. Over the past year, the German Environmental Agency is still somewhat skeptic, somewhat reluctant. They have adapted or adjusted their recommendation, and now they do recommend it a little bit, but not everywhere. And the most thing that is most needed is actually a robust epidemiological big study to see in how far it's effective in preventing the spread of the pandemic, yes or no. I think such a study is still missing, but it's quite difficult to really provide the data. It needs to be really large numbers that are studied in order to really prove the effectiveness of such measures, be it air purifiers, but also venting, how often you vent, or other measures, masks and so on. It's not easy to prove it really on a statistical, very robust level. The public attention has shifted away in Germany a little bit. Omicron is highly infectious, but less severe. Therefore, schools are still open, although the numbers of infections are very high at the moment, and we are at the peak of the Omicron wave at the moment. But yeah, it's not so much discussion anymore. The recommendation based on our study, I would clearly recommend to use air purification in classrooms, also offices, meeting rooms, and so on. It should be Hepa filters or similar. The clean air delivery rate should be as high as possible, with at the same time keeping the noise at a level that is acceptable. So 1,000 cubic meter per hour, I think, is a good value, and less than 45 decibel should be a good number. And there are devices that can do this, especially if you combine several, like 2 or 3 air purifiers, you can easily reach the 1,000 cubic meter per hour and have a low noise level so that it's not really problematic. Energy costs are low for the devices. Maintenance, as I said, you have to look for the filters, but it's not really a big deal. You shouldn't position them behind a curtain or below a table, but this is also obvious, I think. And for the future, even after the pandemic, I think also in terms of reduction of particulate matter, which is super important. Many cities have much too high particulate matter levels, and there are many millions of people dying every year due to too high PM concentrations. This is really also really arguing in favor of filtration for filtering the air and allergens, influenza, and so on as well. Okay, of course, it would be best if every school is equipped with a fixed HVAC system, but as long as this is not the case, I think mobile systems are quite efficient and easy to install. And I think yeah, altogether one has to, of course, to highlight and to emphasize that the best thing is a combination of measures. It's not air purifiers alone, it is air purifiers and ventilation and face masks and rapid tests and so on, all together that provide the best pandemic defense. And this is certainly the combination. The concept is to really bundle the measures, and then you have the best results and the lowest amount of problems. Okay, and this with this, I would like to close the talk and especially express my thanks to Manuel Granzin, Sarah Richter, Nathalie Schubert, and Jan Schroth, who helped a lot with these measurements and participated in the study that we published and also in the follow-up measurements that we did. And with this, I would like to thank you for your attention, and I'm happy to answer questions.
Thank you, Dr. Curtius. My name is Brad. I'm over here at University of Florida. I'm one of the students, and I'll be reading through our questions here in the Q&A. It was a very, very informative presentation. Truly appreciated that, your explanation. We have a lot more than, well, we have about 14 minutes left and a lot more questions than we probably have time for. So for everybody who posted a question, if you posted it kind of early, and the question was largely answered later in the presentation, I may skip over that. If we have enough time, I'll come back, but I'll try to hit the things that may have not been in the presentation. So the first one, Dr. Curtius, is could you comment about the relevance of this work to indoor filtration of wildfire smoke?
Okay, of course, a somewhat different topic, but yes, I think this is definitely similar. You can also reduce the PM indoors by using mobile air purifiers, and you can reduce the smoke, and smoke, of course, is also quite dangerous. Therefore, yes, this is definitely a measure that also works with wildfire smoke.
Thank you. The next question is focused on the outflow from the Hepa filters. So some filters have directional flow, typically out of the top. Some of them have this circumferential, diffuse circumferential outflow. Could you comment about how those two different types of outflow configurations may affect the ability or the impact of those Hepa filters on spreading airborne pathogens within these types of environments?
Well, as we saw, basically, when running air purifiers, especially if you have several and like 4 purifiers running with 250 or 350 cubic meter per hour, actually, you have a turbulent mixing in the entire room. And I think the directional outflow, the important thing is to not blow into someone's face or something, because, well, the air is very pure, so it wouldn't be problematic in terms of pathogens, but it's become, you know, you have a draft and it's cold air, which might be, at least in wintertime, you don't like. In the summertime, it might be like a ventilator, quite a nice thing, but in wintertime, it might be a cold draft. So directing it to the top, I think, is the right thing to do, and in order not to disturb anybody. Otherwise, there were some questions whether, yeah, how far the flow patterns in the room are shifted. I don't think this is really a critical thing. Otherwise, we would also have to be concerned about, I mean, in a school room where you don't know who is the infected person, it's basically impossible to avoid this mixing, and and you always will have some flows that could potentially be problematic going from an infected person to a person that might be susceptible. So I think directing the flow to the roof or to the upgoing direction is a good thing, and there is not much you can change in a typical schoolroom setting, unless you really start installing these pipes that suck out the air and remove it. I mean, unless you really start with a completely directional flow system installed where fresh air is entering like under the seat and then being sucked out at the top, and that's probably even better, but it also means a lot of installment of a lot of things. Okay.
Okay, thank you very much. The next question is looking at the ambient air particulate matter concentrations. So you mentioned the potential impact of that. Did you ever measure it or take it into account over the different days of your sampling?
You mean, did we measure the size of the particles? Or?
Yes. So the size of the particles, just the overall concentration in the ambient environment, how that might have varied from day to day. Was that ever measured?
Yes, okay, we did measure the concentration and also the... There's somebody has the microphone open. Okay, now it's gone. Yes, we did measure the day-to-day variability of the ambient aerosol. It typically varies maybe by a factor of 2, 3 to 3. And we also measured the size distribution, made sure that really in all the sizes the decay is about the same. So yes, we did look at this.
Thank you. A couple of people asked about the clean air delivery rates and how those values were determined. Could you talk about how you measured those?
Yeah, the clean air delivery rate we basically derived by measuring these exponential decays that I showed you. We measure the natural decay without any air purifier and with the air purifier. And from the K value, the decay constant, you subtract these two from each other and multiply by the volume of the room. And then this is the clean air delivery rate. So it's very simple actually to measure it if you have if you start out with this source and then measure the cleaning over time. And actually I see here in the chat there's a question, what was the source in the classroom? The source was really the ambient air coming in, bringing in particulate matter from the outside, and then you close the window and you have a starting concentration from which you start and you clean over time. Okay.
Okay, thank you very much. Have you validated, I guess, in other conditions, the way that the air purifier interacts with ventilation systems?
Yeah, this is somewhat difficult, of course. If you open the window, then you get new aerosol particles in, and it's not so easy to validate this. What I showed was really the calculations. Yeah, you can do it, but we didn't so far really test this mixture of different, I mean, window ventilation plus air purifiers under experimental conditions. It's more difficult to show that you then have a higher removal of the exhaled particles. So we didn't test this experimentally yet. We should think about a setup to do this. And
in the same question box there, did you do any kind of modeling to show, the turbulence of the airflow and how the air may flow between the students in the room?
No, I mean, our group is an experimental group, so we only modeled with assuming perfect mixing. Other groups can do all this modeling of airflows, but we didn't do that. We assumed perfect mixing in our model, in our signal estimations.
Thank you. We've got about 5 minutes left here. Could you elaborate on the infection risk being quadratic instead of using the more typical model, 1 minus the exponential negative dose relationship? And then did you ever look at a critical time for the different setups, perhaps looking at likelihood of infection, 50% likelihood of infection?
Yeah, I hope I get this question right. But I mean, actually the dose is increasing in a closed room quadratically. So this is what I showed here. And of course, here we just looked at 1 hour. Over this hour, we assumed that the virus would stay viable and all the time basically being infected. If you have a virus which dies away within 3 minutes, then this is of course not correct, and you have to include this. This was mostly to demonstrate that the longer you stay in a room with us, and we assumed, I think Van Dormalen has published this, that the virus is still, after several hours, it's still viable or still infectious is a better word. So we assumed that for more than 1 hour, basically the virus can be infectious. This is an assumption here, of course. And yeah, typically aerosols and viruses die away exponentially over time, and this should be included if you would run it for a longer time, yes.
Okay, thank you. It's about 3 minutes. Could you, the one question asked about the percent openable area, so the floor surface area compared to the windows, the space that could be opened. And then if you ever looked at any kind of cost benefit analysis, trying to retrofit all these schools versus just opening windows.
Yeah, I mean, so first of all, the floor area and the window area, I'm happy to send this to Scott McKenzie if he likes. I don't have it in my mind right now, but it should be easy to send it. And then the question about the costs. We estimated, I mean, to equip a room with air purifiers is around, well, let's say for 1,000 cubic meter, you also need, that's as a rough number, 1,000 euros or $1,000 perhaps per room. It's not that expensive if you have 25 students in there. You do need to provide also maintenance, so cleaning the air filters from time to time, the pre-filters, and exchanging filters from time to time. But it's not super costly. I think as long as you stay with these household appliances which are produced in large numbers, the cost is around maybe, yeah, if you double the investment of 1,000, including maintenance and electricity and so on, you end up with maybe 2,000 euros per classroom, or $2,000 approximately. And I don't think this is a very high price. And if you open the windows, at least in Germany, and during winter time, you also have to calculate the additional heating that you need if you do it every 10 minutes for 3 minutes. And this also comes up to several hundred euros per year. So it's also to be taken into account if you open the windows so frequently. Yeah, okay, how the CADR has been calculated, I think we have covered that.
I think we answered that one already. Now, there, to be fair, there are a lot of unanswered questions on the board here, but we have hit 12 o'clock, which was our stopping time. So I just wanted to jump in and say thank you again, Dr. Curtius, again for this informative presentation. And I would open it up to the AAAR folks if they've got anything. Otherwise, if they don't, that would conclude this presentation. So let's give Dr. Curtius a hand.
Okay. Thanks a lot, and I'm happy to provide this.
Yes,
Amy,
thanks
you have-
everyone. Yeah,
Okay.
that was really great.
Great.
Thank you for the wonderful talk and the great job hosting, and thank you all for joining us. And feel free if you have more questions to reach out to our speaker. I'm sure he'd be happy to answer them offline. So
Okay,
thank you, everyone.
Send an email and I'm happy to answer. Okay. Okay, bye-bye.
Thank you. Bye-bye.